Alright, so let's take a look at 12.4, which is determining whether a series is convergent or divergent. We're not going to really go into this one into too much detail. There's really only one key thing to focus on when it comes to determining whether or not a series is convergent or divergent. And it really just boils down to whether or not the series has a sum. If you can figure out if the series has a sum, then it's going to be convergent. If you can't figure out if a series has a sum, another way to approach it is maybe if you can figure out if the series has a limit. Understand that these two concepts are one and the same. If it has a sum, then there is going to be a limit of some sort, whatever that may be. And likewise, if there was a limit, then there must be a sum of some sort. So in both those cases there, the series is convergent. If you're looking at a series and it's not convergent, then it's divergent. So in other words, we can kind of turn that a little bit and say if if a series does not have a limit, or if it does not have a sum, then it's going to be divergent. And so we looked at these three very, very basic examples. The reason why I call them basic examples is because they're arithmetic and geometric, all three of these here. And when you look at that first one, because of the alternating signs, we can tell that our R value is going to be a negative ratio here, and notice that you're multiplying each one of these by a negative half. Now, since that R, that common ratio, is the absolute value of it's less than 1, what that means, this series does have a limit. And it means that those values that you see here are getting, at least their absolute values are getting smaller and smaller and smaller each time when you start to divide those things. And so if you notice that the absolute values of each successive fraction is going to get smaller and it's going to continue to get smaller, it's going to have a limit. So therefore that series of ours is going to be convergent. Taking a look at the next two, notice that this is another geometric series. However, when you notice note the common ratio here, notice that each term is doubling, which means that our common ratio is greater than 1. And if that's the case, then that means there can't be a sum to be found. There's no sum out there, which also means that there is no limit. So therefore the series is divergent. Now, one thing you notice about C here is that we have 10 and then 8.5 and then 7 and 5.5. Careful inspection here, what you notice is that this isn't even geometric. This is actually arithmetic. And that common difference is negative 1.5. Each term is 1.5 less than the next one. All arithmetic series are going to be divergent. Every single one of them. So if you ever notice I throw an arithmetic series your way, know for a fact that it doesn't have a sum, and know for a fact that it's going to be divergent. And so then what we also looked at in 12.4 is if those series were neither arithmetic or geometric, like this one right here. In most cases, I'm not saying all, in most cases you can look at the series and kind of give it the old eyeball test. If you look at that numerator there, it's only going up by 1 each time. You look at that denominator, it's increasing at a faster rate than the numerator is. And so a lot of times you can end up going with your gut instinct there and use just a little bit of common sense and know that this thing is going to eventually have a fraction that's pretty close to 0. And if that fraction is pretty close to 0 and keeps on getting closer to 0, that means it has a limit. And like we said before, if a series has a limit, then it's convergent. So that's pretty straightforward. Let's look at another example, and let's just give it, once again, the old eyeball test. So notice this one right here, 1, and then it becomes 1 over 1 times 2, and then 1 over 1 times 2 times 3. So notice that denominator there is, each term is the next integer's factorial. Once again, the numerator is pretty static there, isn't it? It's not doing much of a change here. It's just going to stay 1. Kind of being sarcastic there. You notice the denominator there, it's going to keep on to increase once you look at all the products there. So this is definitely, given it the old eyeball test, you can definitely conclude that this thing is going to be convergent. We could go through the whole process of trying to figure this thing out. I mean, it's not arithmetic, it's not geometric, but when you do that old eyeball test on that, you're going to notice that the limit is 0. And so if that limit's going to be 0, it's going to have a sum, which means that this series is going to be convergent. Now there was another objective that I wanted you guys to do at 12.4, and that was to be able to look at a series and be able to figure out what the general rule is. So one trick to look for here, and what I stressed to you guys, and you probably, and you'll see this later certainly, is one thing that I've always struggled with in school was, and certainly with series, is being able to figure out that general rule. It became kind of annoying when some other kids would get it a lot faster than I would. But you just got to figure out some of the tricks, and once you figure out some tricks, it starts to go a little bit easier. So one thing I always look for is I try to see if the series as a whole was arithmetic. When you look at the fractions as a whole, moving from one term to the next, it's pretty clear to see that you can't add the same amount each time. Well, then I look at if this thing's going to be geometric as a whole. Looking at all these fractions, notice I'm not multiplying anything here from going from the first term to the second term. I'm not multiplying by anything other than 1. And then realize I'm multiplying by something other than 1, going from 2/4 to 3/8. So when both those fall through, then I shift my focus. And now I start looking at it from this perspective. Can I figure out a rule with the numerator? And then can I figure out a rule with the denominator? So looking at just the numerator here, the first term's 1, the second term is a 2, third term's a 3, fourth term's a 4. So that becomes pretty easy to nail down. I'm pretty sure that we can call that just n depending on what the term is. And then underneath, looking at the denominator, I go from 2 to 4 to 8 to 16. In other words, they're doubling each time. So just the denominator there is geometric, right? We're multiplying each one by 2. So one way I can look at this is the first term. I can say, okay, it's really 2 to the first, right? And then the second term would be 2 to the second, 2 to the third, 2 to the fourth. Cool, so I think we've nailed that. So being able to do that skill right there and be able to nail that down, that's going to be the skill that we're going to be looking at, especially with 12.5. So looking at another example like this one here, once again, let's focus on the numerator, and we can look at that 1, and maybe that first 1, try and look at it from this perspective instead. So when you look at it from this perspective, notice that the numerators are pretty static. If we focus just on the numerators here, no real excitement. So that first term, as well as every other term after that, is going to be a 1. So the numerator, general rule, just put a 1 there. Now you notice the denominator, like we mentioned earlier, was factorial, so we can get away with just writing it just like that. Okay?